Welcome back to this next video in which we are discussing the control of blood pressure and blood volume. Okay, so we're currently looking at a simple model of the cardiovascular system, and we've currently so far built the tubes of the cardiovascular system and we've filled them with 5 litres worth of blood. What we now want to understand is what will happen when we turn the heart on. Okay, so this is where the simple model that we're going to discuss and the more complicated model that we will discuss later are going to differ with how they will actually treat the heart. So in this first simple model, we're going to have the heart behaving very simply. We've already simplified the heart down hugely to just being one chamber which magically oxygenates the blood when it pumps it from the venous to the arterial side, but we're going to simplify it down even further now. So, here is the simple model then that we're going to have of the heart. We're going to have it beating at a certain rate, so we're going to have heart rate nicely fixed. So now that's not too much of a simplification because, you know, heart rate is going to stay reasonably constant, so this is an okay assumption, but the next one is going to be where we are simplifying it down. So we're going to assume that the heart rate is around 75 beats per minute, so the heart's going to beat at approximately 75 times per minute, so 75 times every minute it's going to move a bucket load of blood from the venous side to the arterial side, so that's fine. Okay. Here's where we're going to make an assumption that we will go back on later on in the more complicated model, and the assumption that we're going to make is that the stroke volume, which means how much blood the heart is actually going to move from the venous side to the arterial side every beat, we're going to make the initial assumption that that's going to be fixed, and it's going to be independent of what the pressure in the venous system and the pressure in the arterial system are doing. That's the initial simplifying assumption that we're going to make. We're going to go back on that later on when we come to a more complicated model of the cardiovascular system that we'll need to understand in order to understand the interrelationship between controlling blood pressure and controlling blood volume. But for now, we're going to assume that every time the heart beats, it just moves a constant amount of blood from the venous system to the arterial system, and that amount that it moves does not depend on what the pressure in the venous system and the arterial system are, which of course it really does. But initially, just to get a very simple concept or very important concept across, we're just going to assume that it's constant. Okay, so it's usually around 65 milliliters stroke volume, so that's what we will assume stroke volume will be. Okay, 65 milliliters. Then we might as well introduce another concept relating to the heart, which is the cardiac output, often abbreviated down to CO, and cardiac output is just the amount of blood that the heart moves from the venous system to the arterial system in a minute, and clearly the cardiac output will just be the stroke volume times the heart rate, because this is how many times it beats a minute, this is how much blood it moves with each beat. So if we want to know how much blood it will move in a minute, we just need to multiply this by this, and when you do that you get approximately, so I'll put approximately equal to again, you'll get approximately 5 litres. So it actually moves in a minute the same volume that is in the entire blood system. Okay, the entire blood volume, remember, was 5 litres. Right, so that's the heart. That's our very simple understanding of the heart, that the heart is going to beat at a rate of 75 beats per minute, and every time it does so, it's going to move a bucket load of blood, specifically 65 milliliters, from the venous side to the arterial side. Okay, now, what is that then going to do to the pressure in the venous system and the pressure in the arterial system? Well, of course, it's going to lower the pressure in the venous system because we've removed blood from the venous system, and it's going to raise the pressure in the arterial system because we have put blood into the arterial system. So we will now create a pressure gradient between the arterial system and the venous system, and that is now going to be the driving force for blood to move from the arterial system to the venous system through the microvasculature and perfuse the tissue hence. Okay, so an important equation to know then is an equation that is the foundations of all the fluid mechanics, which is that the flow is equal to the difference in pressure, the pressure gradient, divided by the resistance of the blood vessel. Okay, so this symbol here, which is a capital Phi, a Greek symbol, this is often used for flow. So this is the amount of blood, the volume of blood that is flowing through a vessel in a certain amount of time. This is going to be equal to the pressure difference between the two sides of the vessel divided by the resistance of the vessel. And this makes sense. The bigger you make the pressure difference, the more blood is going to flow. The bigger you make the resistance of the vessel, i.e. how narrow you make the vessel, that's what this number is reflecting here, the smaller is going to be the flow, hence why it's in the denominator there. So it's a very intuitive relationship to be true, that flow is going to linearly depend on the pressure and then reciprocally depend on the resistance in this way. Okay, so when you create then a pressure difference between the arterial system and the venous system, you're going to get blood moving from the arterial system to the venous system through the microvasculature, and that will be perfusing the tissue. Okay, now, here's a really important thing to understand. When we start this from the beginning, so remember we've started off with the heart being off and the blood was evenly distributed between the arterial system and the venous system and all over the cardiovascular system, and the pressure everywhere was just 7 millimeters of mercury, the mean systemic pressure. When we start the heart at this with these specifications, so the heart's going to work to these specifications, what is then going to happen? Okay, well the heart's going to do its first beat and it's going to move 65 milliliters of blood from the venous side to the arterial side. Then it will do its second beat and it will move another 65 milliliters of blood from the venous side to the arterial side. The question that I want you to consider is, by the time the heart does its second beat, which will be after 0.8 seconds from the first beat commencing, because a rate of 75 beats per minute is a cycle duration, a time for each beat. That's another important concept. Cycle duration just means the time taken for each beat of the heart. That will be 0.8 seconds. So 0.8 seconds after the first beat commenced, we'll have the second beat commencing. Okay, the question is, when the heart beats for the second time, will all of the blood that it moved in the first beat have had the opportunity to move back from the arterial system to the venous system? i.e., will the whole thing have had time to reset between the consecutive beats? And the answer is no. The heart is beating very rapidly, and in that time you do not move all of that 65 milliliters of blood back from the arterial system to the venous system. If you waited long enough, of course, it would have all moved back from the arterial system to the venous system, and you would have returned to this beautiful steady state where there's just 7 millimeters of mercury pressure everywhere. Okay, however, that you don't return to this, the initial state, in 0.8 seconds between the two beats. You don't have a high enough pressure difference here to drive a fast enough flow through the microvasculature to return the 65 milliliters that the heart has beat from the arterial system to the venous system. So that means that when the heart beats for the second time, some of the blood that it beat over in the first time will still be in the arterial system and missing from the venous system. So we haven't gone back to our beginning situation. Instead, what's going to end up happening is gradually the arterial system pressure is going to build up and the venous system pressure is going to fall down. So do you understand what I'm saying? That with each beat of the heart, we're going to be gradually moving, we're going to be gradually ending up with more and more blood in the arterial system and less in the venous system, i.e. we're going to build up higher and higher pressure in the arterial system and a lower and lower pressure in the venous system. But of course this will be building up the pressure gradient, so with each beat of the heart we'll be building up the pressure gradient here, and that means that the flow from the arterial system to the venous system is going to increase. Okay, so we will eventually reach a dynamic equilibrium. We will eventually get the pressure difference between the arterial system and the venous system to such a level that the amount of blood that flows from the arterial system to the venous system, because of that pressure gradient in the cycle duration of 0.8 seconds, is going to equal the 65 milliliters that the heart moves across. So I hope you understand what I've just been talking about. I've been talking about the fact that as you let this system run, what will gradually happen is, because you haven't initially got the adequate pressure difference between the arterial system and the venous system to get a flow from the arterial system to the venous system of 65 milliliters in the 0.8 seconds, you're not going to have it in equilibrium initially. You're going to be moving more blood from the venous side to the arterial side through the heart than you are moving back through the microvasculature. It will reach an equilibrium when we get to a high enough pressure gradient between the arterial system and the venous system that the flow of blood back from the arterial system to the venous system in 0.8 seconds, because of the pressure gradient, is equal to the amount that the heart moves across in that 0.8 seconds. That's the point that we reach dynamic equilibrium. Okay, so that's the next concept that we need to understand, that eventually this cardiovascular system will reach a dynamic equilibrium where we have a large enough arterial pressure and a low enough venous pressure, that we have a large enough pressure gradient between the two, that the amount of blood flowing from the arterial system to the venous system in that 0.8 seconds matches the amount that the heart will move in that 0.8 seconds, which is 65 milliliters. So we're going to reach a dynamic equilibrium. Now the question is, how high does arterial pressure have to rise and how low does venous pressure have to go at this equilibrium? What are the pressures that you have in that equilibrium? Well, this is an important point that we need to understand now. Arterial pressure, the pressure in the arterial system, that varies hugely at different points of the cycle. When the heart has just forced blood into the arterial system from the venous system, the arterial pressure is at its maximum. And then when the blood is moving from the arterial system back to the venous system and the heart isn't pumping more blood in during the relaxation period of the heart, then the arterial pressure will be falling. So arterial pressure isn't constant, it varies at different points of the cardiac cycle. So there is the concept then of systolic pressure, and I'll just make sure this is straight, which it isn't. So there is the concept of systolic arterial pressure, which we'll just call systolic pressure, okay, which is usually abbreviated down to SP, and there is also the concept of diastolic pressure. Okay, and these are both pressures in the arterial system, and we are now talking about the pressures of these at equilibrium. Okay, so we've reached our dynamic equilibrium where the amount of blood moving from the arterial system to the venous system in that 0.8 seconds during each cardiac cycle matches the amount of blood that the heart is moving from the venous system to the arterial system, which is 65 milliliters. So we're at the dynamic equilibrium, and even once we're there, we do have arterial blood pressure fluctuating because there is systolic pressure, which is the pressure in the arterial system just after the heart has pumped the blood into the arterial system. So that's the maximum one, and at this dynamic equilibrium, this is approximately, in a healthy person, 120 millimeters of mercury, so much greater than the mean systemic pressure here. Okay, so that's normal systolic pressure then. And then there is diastolic pressure, which is the smallest blood pressure in the arterial system. That's the pressure just before the heart is about to put the stroke volume's worth of blood into the arterial system. So just before the heart contracts, once we're right at the end of diastole and a lot of blood has moved back from the arterial system to the venous system through the microvasculature, that's when we have the lowest blood pressure in the arterial system. This is known as diastolic pressure, and this is generally around 80 millimeters of mercury. So blood pressure in the arterial system does vary considerably in that 0.8 seconds of each of the cardiac cycles. Okay, another related concept here is the concept of pulse pressure, which I might as well introduce you to now. So the concept of pulse pressure then is the difference between systolic pressure and diastolic pressure. It would just be written pp, and it would therefore approximately be 40 millimeters of mercury. I've just taken systolic pressure and subtracted off diastolic pressure there to get pulse pressure. Okay, now another really important concept is the concept of mean arterial pressure. Okay, so this is usually just abbreviated down to MAP, and this is the one that throughout the video from now on we will be talking about rather than systolic pressure or diastolic pressure. Okay, so mean arterial pressure is what this stands for. Now, you might think, from your knowledge of basic maths, that mean arterial pressure would just be 100, because all you do is take the mean of systolic and diastolic pressure, but that is not what you do. Okay, mean arterial pressure, you'd add these two together and divide by 2 to get 100. That's not what you do. The concept of mean arterial pressure is cleverer. The concept of mean arterial pressure is it's the pressure that you'd have to have in the arterial system, and if you kept this in the arterial system continuously, then in 0.8 seconds you would move the same amount of blood as you would with it actually fluctuating in this way. So let me explain a little bit better than that. So in each cardiac cycle, which lasts 0.8 seconds, we have the heart pumping the blood into the arterial system. And let's say that right at the beginning of the 0.8 seconds, the heart has pumped the blood into the arterial system. Then throughout the rest of that 0.8 seconds, if I draw a little graph of this, okay, let's have a little graph here. So let's have time along the x-axis, and let's have arterial pressure, which I'll just put as AP here, on the y-axis. So at the beginning of the 0.8 seconds, let's say this is 0, and right at the end here can be 0.8 seconds. So at the beginning, we are raised up from diastolic pressure, which is here, let's say, which is around 80, up to systolic pressure, which is here, which is around 120. Then, throughout the 0.8 seconds, pressure will be falling, like so, down back to diastolic pressure, okay? And that's because blood is moving from the arterial system to the venous system. Now the flow, the rate at which blood is flowing from the arterial system to the venous system through the microvasculature is going to change at different points of the 0.8 seconds. Okay, so it is not just a straight line, and the reason it's going to change is because, of course, the pressure gradient changes as the arterial pressure falls. And why is the arterial pressure falling? Well, because blood is flowing back from the arterial system to the venous system. So there is a complicated relationship on this graph. It is not a straight line descent from systolic pressure to diastolic pressure over the 0.8 seconds. That's the main point that I've wanted to get across there. I have not drawn a straight line. The rate at which we are descending is most rapid at the beginning when we have the highest pressure in the arterial system, because then the pressure gradient is going to be highest, so we'll have the most flow back, and then it's going to get lower as we go down to diastolic pressure. Okay, so, however, over the 0.8 seconds, how much blood will actually flow from the arterial side to the venous side? Well, we said we're at this dynamic equilibrium, so the amount that will flow is 65 milliliters, so that it matches the amount that the heart is moving, has moved across at this point, and therefore we are in an equilibrium. What is meant by the mean arterial pressure is it's the pressure that you would need to have in the arterial system continuously to produce the same amount of flow as this relationship did have. So we have, in reality, we have the fluctuating pressure in the arterial system, and that produces this flow of 65 milliliters. If we wanted to simplify it down and have a constant pressure in the arterial system all the time, a straight line graph here, what pressure would we have to have in order to get the same amount of blood flowing from the arterial system to the venous system? That is the concept of the mean arterial pressure here. Okay, so I hope you understand what that is, and I hope you also understand why it's not just this one plus this one divided by 2. If this pressure, if this line of how pressure varies over the 0.8 seconds just followed a straight line graph, i.e. a straight line down from SP to DP, then it would be, the mean arterial pressure would be 100, but it's not. In reality, it's less than 100. It's around 93 millimeters of mercury, and I'll give you a formula in just a moment for how to work that out. In fact, actually, I'll give you a formula to work that out in a moment, right now, in fact. So, mean arterial pressure, the formula that approximately gives you it is if you take diastolic pressure and add on to it a third of pulse pressure. Now this is an approximation, this is not an exact formula. This is a formula that approximately gives it to you. Okay, if you actually wanted a mathematical formula that gave it to you, you would end up with a much more complicated formula, and even then it would just be a mathematical model. Okay, but this is an approximate formula that you can use to get that. Okay, so hopefully you can see that if you put in the numbers here. So if you put in 80 for diastolic pressure and then put in 40 for pulse pressure, you approximately get 93 millimeters of mercury. Okay, so mean arterial pressure means what pressure would you need to have in the arterial system for the entire cardiac cycle between 0 and 0.8 seconds to get the same movement of blood from the arterial system to the venous system as you do get in reality with this fluctuating pressure where you're starting at systolic pressure and then going down to diastolic pressure. Okay, that's the concept of mean arterial pressure. One other important concept before we can go any further is the concept of mean venous pressure. Okay, and this is, of course, just as the name says, the mean pressure in the venous system now. So MVP means mean venous pressure. And of course, at this dynamic equilibrium, we are interested in what is going to be the mean venous pressure because we know it will have decreased from the systemic pressure, the mean systemic pressure that we started off with of 7 millimeters of mercury because we have taken blood out of the venous system. Now, the mean venous pressure is much more simple than the mean arterial pressure because venous pressure doesn't really vary with the cardiac cycle. So that's one thing that's much simpler about this. It's just really constant. The other thing to warn you about is you'll look at this and look at mean arterial pressure, which is effectively the effective pressure in the arterial system. If you wanted to simplify your understanding of what arterial pressure is down, you'd use this, and indeed we will be using this throughout the video, rather than remembering that the pressure does fluctuate within the cardiac cycle. We'll just think of generally arterial system pressure is this mean arterial pressure, and you see it's much, much bigger than the mean systemic pressure. Mean venous pressure is not going to be that much of a drop from mean systemic pressure, and generally at this dynamic equilibrium it's going to be around 5 millimeters of mercury. So now you might be wondering, well, how have you raised mean arterial pressure so much, i.e. from 7 millimeters of mercury, which is what it was when we were in the initial state, to 93 millimeters of mercury, and yet you haven't dropped mean venous pressure that much at all? Well, remember me telling you that the venous system is enormous compared to the arterial system. You have a lot more blood in the venous system than in the arterial system. So moving, a very small fraction of the blood from the venous system to the arterial system has a very small effect on venous pressure, but a very large effect on arterial pressure. And that's why we see these apparent discrepancies here. Okay, right, so to go over it then. When you have the heart functioning with these specifications of a heart rate of around 75 beats per minute, a stroke volume of around 65 milliliters to give us overall the cardiac output of around 5 liters, we reach a dynamic equilibrium of arterial pressure and venous pressure. And the effective arterial pressure that you can imagine having continuously, if you're too stupid to remember, such as I am, to bother with thinking about systolic pressure and diastolic pressure, is around 93 millimeters of mercury. So effectively, if you just want to imagine that the arterial pressure is constant, this is the effective constant value for the arterial pressure. The amount of blood flow that you'll get from the arterial system to the venous system will be the same as you really do get with the alternating pressures, if it was the case that the arterial pressure just remained at this mean arterial pressure of 93 millimeters of mercury. Meanwhile, the mean venous pressure, which really is quite true to think about that because that does remain reasonably constant, is around 5 millimeters of mercury. So now, a formula then. At this dynamic equilibrium then, the flow from the arterial system to the venous system is going to match the cardiac output. So the cardiac output, which is the flow from the venous system to the arterial system through the heart every minute, which is around 5 liters, is going to need to equal the flow from the arterial system to the venous system. And remember, you can imagine that the arterial pressure remains at this throughout the entire minute. This is why this is such a beautiful concept, because this effectively captures this much more complicated reality really simply. So it's going to be the pressure gradient between the arterial system and the venous system, and the effective pressure in the arterial system is the mean arterial pressure. We then just subtract off the mean venous pressure. This is effectively delta P, and we then need to divide it by the resistance. Okay, and the concept for the resistance of the microvasculature is the total peripheral resistance. So this is another really important concept here. TPR, this means the total peripheral resistance. Now, of course, how on earth do you work this out? Well, generally the way you actually work this out is you find blood pressure, you measure blood pressure, you measure cardiac output, and then you can work out total peripheral resistance from that. But as a theoretical concept, it is an important concept. So total peripheral resistance, even if it's only measurable indirectly by this formula. Okay, total peripheral resistance. So this means how much resistance to flow does the microvasculature put up. So if the microvasculature, for instance the arterioles, these are capable of vasoconstricting or vasodilating. So arterioles have a layer of smooth muscle cells around them which can constrict them, or they can relax down and therefore dilate the arteriole. If loads of arterioles all around the body were to suddenly vasoconstrict and reduce the diameter of their lumens, then overall the microvasculature would now put up much more resistance to flow, and therefore the total peripheral resistance of the cardiovascular system would have increased. If the arterioles all suddenly dilated, loads of arterioles of the microvasculature all over the body suddenly dilated, then that would now hugely reduce total peripheral resistance. And of course, total peripheral resistance will have units to make this work, because cardiac output, that will have units of, let's say, litres per minute. The pressures that we're using here we'll use in millimetres of mercury, so you'll have to just make this have the correct units to make this all work. Okay, but the actual function of this equation isn't that important. It's nowhere near as important as the concept that it gives you. Okay, so this equation isn't about actually being able to plug in numbers and get out answers. Really, the importance of this equation is the concept that is involved here. Okay, that the cardiac output must be matched to the amount of blood that is flowing from the arterial system to the venous system, and how much blood flowing from the arterial system to the venous system is dependent upon what the pressure gradient between the two is and how much resistance there is between the two. What these numbers actually are, that doesn't really matter. Okay, it's the concept that's important. I mean, why would you want to work out these numbers, frankly? The concept is what's important. And I'm really referring to total peripheral resistance here, and the fact that, the units, if you were using different units for pressure and different units for cardiac output, then you just alter the units of total peripheral resistance, and obviously alter the number as well, based on those units. So what I'm really saying here is a justification for why I'm not about to give you a value for what total peripheral resistance usually is, because you could use so many different units, and in those different units it would have very different values, and it would vary depending on different people and depending on their current states. Okay, but it's the concept that's more important here. Now, a simplification of this formula then is, because mean venous pressure is so low compared to mean arterial pressure, why don't we just get rid of it from that formula? And now we just end up with this much simpler formula, which is just cardiac output is approximately, and I should put approximately here, approximately equal to mean arterial pressure divided by total peripheral resistance. Okay, and this is a really nice formula, because what we can do with this is now use a little bit of algebra here and rearrange this, and what we can get now is that mean arterial pressure therefore is equal, or is approximately equal to, cardiac output times total peripheral resistance. So this means that if we want to maintain a constant mean arterial pressure, we need to maintain a constant cardiac output and a constant total peripheral resistance. And if one of these changes, so for instance if total peripheral resistance was to suddenly change, maybe all the loads of arterioles somewhere were suddenly to dilate, and we want to maintain a constant mean arterial pressure, which is very important for maintaining the same amount of blood flowing through microvasculature in certain tissues, then we're going to have to raise cardiac output. So this relationship is going to be very, very important here. Okay, so we will have a break here, and in the next video we'll go on to the more complicated model, but before we just take our break, let's just summarize this simple model here. So, the heart's role is to maintain this pressure difference between the arterial system and the venous system. At dynamic equilibrium, we have a high pressure in the arterial system, and effectively the mean arterial pressure here is around 93 millimeters of mercury. We have a low pressure in the venous system. The mean venous pressure is around 5 millimeters of mercury. This means that if you take a microvasculature circuit or a little microvasculature network in a certain piece of tissue, let's say we go to a piece of liver maybe, or maybe a piece of brain, a better example, a piece of brain, and we've got one of these microvasculature networks here where we've got an arteriole splitting into a capillary bed splitting into a venule, okay, and we want to maintain a constant blood flow through that, then we need to maintain the pressure in the arterial system and the pressure in the venous system. If you keep mean arterial pressure and mean venous pressure the same, then you'll always be getting the same amount of blood flowing through this microvasculature network at that specific portion of brain, and therefore that specific portion of brain will have a constant perfusion. So the heart's job, therefore, is just in maintaining mean arterial pressure. If the heart maintains mean arterial pressure, then blood flow to the different portions of the body will remain constant. Through these microvasculature networks in the different portions of the body will remain constant. Okay, now, finally then, we saw this formula here which tells us how the heart is to maintain mean arterial pressure, because of course the heart controls cardiac output. So if total peripheral resistance was suddenly to change, so for instance, if loads of the arterioles in the skeletal muscle cell, in the skeletal muscle tissue rather, were suddenly to start dilating because you're about to exercise and you need an increased blood flow to the skeletal muscle, that would hugely reduce total peripheral resistance. If we're going to maintain a constant mean arterial pressure, which we need to do so that microvasculature network up in the brain gets the same amount of blood flowing through it in a minute, then we need to also raise cardiac output, is what this formula is telling us. And that's the great lesson then of this simple model of the cardiovascular system. In the next video, we will go on to a more complicated model of the cardiovascular system, which now gets rid of this nice simplification that we just assume that the stroke volume is constant and does not depend on what the mean venous pressure and the mean arterial pressure are, whereas the reality is, of course, it does depend on what the mean venous pressure and the mean arterial pressure are, and we need to understand that in order to understand the importance of controlling blood volume for controlling blood pressure.